Hey there! Today we're going to tackle one of the biggest stumbling blocks in all of chemistry, the limiting reactant. It's that one concept that seems to trip up almost everyone at some point. But trust me, getting this down is the key to understanding how chemical reactions really work. So let's just dive right in.
Does this feel familiar? Yeah, you are not alone. It is an incredibly common frustration, and you know what? It almost always comes down to one or two tiny, super easy to fix mistakes. By the end of this, you are going to know exactly what they are and how to dodge them for good.
Okay, before we even touch the math, let's connect this whole idea to something we can all understand: baking cookies. Because really, when you get down to it, a chemical equation, it's just a recipe.
So, what even is a limiting reactant? Well, think of it this way. It's the ingredient you run out of first. That's it. It's the one thing that gets totally used up, and because of that, it's the boss. It single-handedly decides the absolute maximum amount of stuff you can possibly make.
Let's just break this down with our cookie example. Your recipe calls for 2 cups of flour, but you've only got 1. Now, you might have tons of sugar and a whole carton of eggs, but it doesn't matter, right? You're going to run out of flour first, and that means you can only make half a batch of cookies, tops. That flour, that's your limiting reactant. It dictates the entire outcome. And guess what? It works the exact same way in chemistry. So, how do we actually find the limiting reactant in a chemical reaction without falling into those common traps? Well, it is definitely not a guessing game. There's a simple, foolproof, 3-step method that's going to work for you every single time. Let's walk through it.
Here it is. Step 1, and this is non-negotiable. You have to make sure your equation is balanced. Step 2, and this is absolutely critical. You have to convert everything to moles. Moles are like the universal currency in chemistry. They let you compare apples to apples because they represent the actual number of molecules doing the reacting. And finally, step 3. Take the moles you just calculated for each reactant and divide that number by its coefficient. The big number out front in the equation. Whichever reactant gives you the smallest final number, that's your guy. That's the limiting reactant.
Okay, let's try this out, making some water. The equation is balanced, 2H2 plus O2. We start with 10 moles of hydrogen and 8 moles of oxygen. So for hydrogen, we take its 10 moles and we divide by its coefficient, which is 2. We get 5. For oxygen, we take its 8 moles and divide by its coefficient, which is just 1. We get 8. And there it is. 5 is smaller than 8, so hydrogen is our limiting reactant. And that's the key right there. Hydrogen is going to run out first, even though we started with more moles of it.
And that brings us perfectly to the single biggest mistake people make with this topic. I call it the stoichiometry trap. And falling for it is the #1 reason students do all the math right but still get the wrong answer.
So here's the trap. You cannot just look at the starting number of moles and pick the one that's smallest. If you do that, you're completely ignoring the recipe, the stoichiometry, which tells you the ratio of ingredients you need. It's such a tempting shortcut, I know, but trust me, it's a trap every time.
Check out this perfect example. We start with 12 moles of iron and 12 moles of water, the exact same amount. So you might think there is no limiting reactant. But wait, the recipe says we need 4 water molecules for every 3 iron atoms. So when we do the math, for iron we get 12 divided by its coefficient, 3, which is 4. For water, we take its 12 moles and divide by its coefficient, 4, which is 3. 3 is smaller than 4, so water is the limiting reactant. This just proves you cannot just eyeball the starting amounts. You have to do the math.
Okay, so now that we've totally nailed the core method, let's see how this skill pops up in a couple of other common areas: reactions that happen in solutions, and when you're calculating percent yield.
The good news is the method doesn't change, even when the problem looks a little different. See, for reactions in solutions, you're not usually given grams. Instead, you'll use the formula molarity times volume to get your starting moles. But once you have those moles, you just do the same 3-step process. And listen, this is so important for percent yield. Your theoretical yield, that's the absolute max amount of product you could ever hope to make, it must be calculated using the limiting reactant. If you use the other one, your whole calculation's going to be way off.
All right, let's do this. Let's run through a big example from start to finish. This one's got it all, starting with mass, a tricky reaction, and calculating the final product. This is where every piece of the puzzle comes together.
So, the problem is we're burning 15 grams of ethane with 32 grams of oxygen. Now, what's our first step? It's not to compare 15 and 32. Remember the golden rule? We have to convert everything to our universal currency. We gotta find the moles.
Okay, so for each one, we take its mass and divide by its molar mass. For ethane, 15 grams turns out to be half a mole, and for oxygen, 32 grams is exactly 1 mole. Perfect. Now we have numbers we can actually compare. Let's move on to step 3.
Time for that crucial division step. For ethane, we have 0.5 moles, and we look back at the balanced equation, its coefficient is 2, so 0.5 divided by 2 gives us 0.25. Now let's see how oxygen compares to that.
Now for the oxygen. We started with 1 mole, but its coefficient in the recipe is a whopping 7. 1 divided by 7 is about 0.143. And there we have it. We compare our two results. 0.143 is definitely smaller than 0.25. We found it. Oxygen is our limiting reactant.
And because oxygen is the limiting reactant, every final calculation we do has to be based on that starting amount of 1 mole of oxygen. We use the recipe's ratios to figure out how much product we can make. And when we do that, we find that the absolute maximum amount of carbon dioxide we can produce is 25.1 grams. That is our theoretical yield.
You know, mastering the limiting reactant isn't just about getting through one chapter or passing one test. It's really about building a foundational skill that is going to show up over and over and over again for your entire journey through chemistry.
So what's the bottom line here? The key is to be systematic. Do not take shortcuts. Always follow the 3 steps. Always balance that equation, always convert to moles, and always divide by the coefficient. If you just build that habit, you'll get the right answer every single time.
Look, in the end, finding the limiting reactant isn't just about crunching numbers to get the right answer. It's about understanding constraints so you can unlock potential. It's about knowing exactly what's holding a reaction back so you can predict what you can create. This is way more than a calculation, it's a completely new way of seeing the chemical world. Thanks so much for joining me.